And also, thank you, Rita Nauer, for the introduction. I'm going to extend it a little bit what Richard explained. So, well, first, what I'm doing, this talk is going to be about ultrasound flow mapping for the investigation of crystal growth. This is a joint work of our group, Solar World, who produce solar cells, and the University of Freiberg, who are experts in mining and materials in general. So the motivation for this talk is to produce high-quality solar cells, and to produce high-quality solar cells, we need to understand the process, how they are produced. So the process we want to improve is a directional solidification process. Directional solidification means we have a rectangular shaped crucible. This crucible is filled with liquid silicon, and we solidify the silicon from the bottom to the top and grow the crystal like this. So during the process, during the solidification process, we have a magnetic field which is caused by the heaters, so it's a parasitic magnetic field which causes a melt flow, and we have a temperature distribution which has an influence on the solidification, and further both melt flow and solidification influence each other. So to understand this, usually numerical simulations are run, but these numerical simulations, there are a lot of parameters to choose, and especially when it comes to simulating the turbulence, it gets difficult, and you can't tell what's right and what's wrong. Even experts can't really tell without looking into the melt. So we need a measurement to calibrate the numerical simulations, but silicon has a melting point of about 1,400 degrees Celsius. So as far as I know, there are no ultrasound transducers working at this temperature, so we can't measure at this temperature. So the idea is we take the industrial process and transfer it to the laboratory to a low temperature model experiment. So this is the part which the University of Freiberg has done to transfer the industrial process to the model experiment and to build this model experiment. We have the measurement techniques, and here we use them to do a flow mapping to understand the melt flow and do a solidification from tracking. To do that, we have this ultrasound array Doppler velocimeter. I'm going to present this measurement system, and I'm going to present the FPGA signal processing, which we are doing to run this long measurements for solidification processes. Not a thing which takes just a few minutes, it takes hours to run the solidification experiments. In the next chapter, I'm going to present the application, the model experiments, and what we have measured there, the flow mapping and the solidification front tracking, and then I'm going to conclude my talk. So first, about the transducers we used. On the left side, there's a picture depicting the model experiment. So we have a crucible filled with gallium. Part of it is solid, part of it is liquid. Gallium is the model fluid we are using instead of silicon. We have a cooler and a heater, and we have a melt flow inside the liquid gallium. So first we want to measure the melt flow, therefore we have ultrasound arrays. These are no phased arrays, these are arrays with fixed sound field. The element size of these arrays is 5 × 5 millimeters, so way above the wavelength. Each of these arrays has 42 elements, so we can get a 2-dimensional velocity field of one component, and to get a vector field, we use 2 arrays on each plane to get both velocity components. Well, then we want to do the solidification front tracking. Therefore, we have 9 transducers placed on top of the melt. The transducers are mounted inside the heater like this. We need 9 sensors because the solidification front is not just a plane which is moving from the bottom to the top. It has a shape which is not always what we intend or not as we expect, so we need to measure the position and the shape of the solidification front. About our measurement system to drive these sensors, it's based on pulsed wave ultrasound Doppler. With the sensors in this configuration, we get a 2.5 dimensional two-componential flow mapping, and the core of, or the heart of our measurement system is our custom multiplexing electronic, which manages the whole measurement process, which does the timing and which controls everything around it. So what does it do? We have burst signal generation, which it has function generators with amplifiers, and the amplified signals are mapped by the multiplexing electronic to the ultrasound transducers. The echo signals are mapped back to FPGA data acquisition and signal processing. So part of this measurement system is connected to the flow mapping, and the part is used for the solidification front tracking. We can't measure with all elements at the same time because then we would have acoustical crosstalk and wouldn't work. So we use time division multiplexing with a parallelization to get a high temporal resolution, but we can't drive all the elements at the same time. So this is how it looks like. In this example, we have 4 active elements at one time. Now here, in this configuration, we now need 36 analog channels, and these channels are sampled at 32 megahertz with this FPGA, and 36 channels times 32 megahertz is quite a lot of data, so we can't just store it like this. We need online signal processing. Our signal processing, I think I can do this quite fast. We do an IQ, we get the echo signals, we do an IQ demodulation, and then we have an autocorrelation based velocity estimator, and later we can visualize it. For our measurement configuration we are currently using, we get a data throughput of about 1.5 gigabytes per second, and after the IQ demodulation, it's reduced by factor of factor 10, and which means we get 120 megabytes per second. This is the amount of data we can at least store and process it later. So we took the part of the IQ demodulation and implemented it on an FPGA to enable long-running measurements of multiple hours. Our application already said some words about it. Now to look a bit in detail, our model experiment. So on the left side, you can see the model experiment is here, this small part. The orange-brown stuff are the coils to drive the magnetic field, and here's the current source which generates the magnetic field together with the coils. And here we have our measurement system. And now to look a bit closer at the model experiment, we have these coils, which you can also see here. And then inside there is a crucible made out of glass filled with gallium. In this case, it's currently liquid. Yes. And we place, when we start the experiment, we place the heater on top of it to heat it, or at least to have a certain temperature distribution for the solidification experiments. So what we get now for a measurement. This was measured at an alternating magnetic field. And yeah, what you can see is basically there's turbulence, but you can't really tell from the flow what's happening. At least it's quite hard to tell from the time-resolved flow. And actually, for the numerical simulations and for the process, for the silicon process, it's important to look at the mean flow. The mean flow gives us information about the material transport and the heat transport. And we need a good material and heat transfer in the melt. So actually we are interested in the mean flow, and this is how the mean flow for this measurement looks like. So just another example of how the flow can look like. It's a mean flow again on the left side. For another alternating magnetic field, we now changed the frequency. Before we had a frequency for the magnetic field of 50 Hertz. Now it's 205 Hertz. And our colleagues at Solar World did numerical simulations. They had about 7 models, and out of the 7 models, they choose the one with the best agreement, which was this one. Other models didn't show any agreement. The flow looked completely different. There were greater quantitative differences. So this was the one best working for this flow. Now about the solidification measurements. The previous measurements were without solidification, so we just had our melt, 100 millimeters of gallium melt, and now we started to set our temperatures. The temperature at the cooler we set to 8 degrees. The melting point of gallium is at about 30 degrees, so we started the solidification. And for the solidification, for an example, we got this shape. It's an inclined shape, and actually we used a traveling magnetic field here. A traveling magnetic field leads to a flow structure, a flow shape, which looks like this. So we get a toroidal flow pattern, which should lead to a W-shaped solidification front, and we didn't get it here. This is probably, quite sure, this is a problem of the model experiment. We need to improve the model experiment to be more accurate, to get what we expect from the theory. But at least what we can tell, the ultrasonic measurement did work. And just to show an example of the measurement, how the solidification front progresses over the time. So for the solidification process, we have the height of the solidification front plotted over the time. So after about 2 hours, the solidification front is grown, about 25 millimeters. Yeah, to come to the end of my talk, I want to conclude. I presented the ultrasound array Doppler velocimeter, which is able of doing comprehensive flow mapping. Thanks to FPGA signal processing, we can run multiple hour measurements, which is required for the solidification experiment, and we are able to do solidification front tracking. So far we were already able to prove some numerical models. It's still in work that Solar World proves more numerical models, and for sure they are not going to present them all. Yeah, and the outlook, Richard Nauber already told, we are going to use the new phased array measurement system to apply to the solidification experiments to get a more detailed information of the solidification front. Well, thank you for your attention.